So what we're gonna do today is we're gonna show a lot of application of MaxFlow. We worked quite hard last time to show some polynomial time algorithm for MaxFlow. And today we just gonna solve 10 problems and prove 5 more theorems using MaxFlow. It's very powerful. Okay, but let me first recap. So in the MaxFlow problem, right? You have a directed graph, and you have a node S and T, and there is a capacity on every edge, like this. And what you want is to send flow from S to T, and the flow must have, you need to have flow conservation on every node, which is not S and T. And the flow going through any edge need to respect the capacity. And you want to maximize that flow. And just to be more formal, we need a flow here, right? That respect the capacity. So the flow is at most the capacity on every edge. And also for every node here, you have flow in equals to flow out. And so this for the skew symmetry here, this is just for notation. Don't need to worry about it that much. And the value of the flow that we want to maximize, last time I said that it's just flow out of S. That is actually when I assume that there is no edge into S. Actually, it should be the net flow that go out of S. So flow out of S minus flow in of S. So if there is some edge going into S and you send some flow into it, then that count as minus the value of the flow. You want to count the total net flow going out of S. But normally we usually think S has only outgoing edges, and if that is the case, then there is no inflow anyway. Okay, and yeah, and the net flow out of S will be the same as the net flow into T, because of you have flow conservation. Okay, so that's the goal. We want to find the flow with maximized value. And you also know we learned about ST cut, which is just a set that contain S and not contain T. A is on S is on the A side, T is on the B side. And the total capacity of edges is the cut size. You count the total capacity of edges from A to B. And we learned last time that for any graph, for any S and T, ST min cut is the same as ST max flow. So that's the theorem, and we're gonna see why it's so powerful today. Also, we learned how to compute max flow, and using 2 algorithms for focus and ND-nits. And if the capacity are integer, they will return integral flow as well. So the flow on every edge is the integral value. You also see that if you have max flow, you can compute min cut fast. Okay. All right, so that's just to recap what we have from last time. Now, let's try to solve some problem. So this problem is kind of similar to what we have seen. So let's see. Let's start with this. In this problem, it's called minimum edge cut. You have the directed graph and 2 nodes S and T. And now I asked you, what is the minimum set of edges so that after I delete these edges, then you don't have directed path from S to T. So S cannot reach T. For example, this is a min edge cut in this graph. You can delete just 3 edges, and S cannot reach T. Okay. So, okay. Any suggestion how can we solve this problem using MaxFlow? Okay.
Make all the entries 1 and then min cut.
Yeah, exactly. We can set the capacity. Yeah, capacity of every edge to be 1, right? And then And then you just compute max flow in this graph. Given max flow, you can compute min cut. Let's say this is a cut, ST cut AB. This ST cut is exactly the cut that minimize the number of, minimize the capacity of it. In this case, the capacity is 1, so it just minimizes the number of edges going out of it. And once you delete these edges along going out of a cut, there's no way that S can reach T. So just compute minimum ST cut in the graph with capacity 1, you get the min cut that disconnect S from T. Good. Well, how about this? Next problem. It's called edge disjoint path. So you have directed graph G and also the ST node ST. And now what I want is a maximum set of edge disjoint path from S to T. So look at this colored path. For example, these are 3 paths that don't share any edges. They cannot share any edge from it with each other. Okay. And you can see that similarly from the same reason, right? Just again, try to reduce it to flow problem just by set the capacity of everything to 1, and so max flow. And let's say I solve integral max flow. So that is, here now I will get a flow such that every edge have value only 0 or 1. And now I claim that, okay, I get some flow. I claim that now from this flow, I can decompose this flow into a set of edge disjoint paths. Okay. And we're going to see how. But once you just return this set of, decompose the flow into a set of paths, just return that set of paths and we're done. So let's see a bit, how can you decompose flow into paths, right? So imagine that someone gives you a flow, ST flow like this. There's no path given to you. It's just a bunch of flow. Like this is the edge with flow on it. This is no flow on it. Okay. Now, let's consider just the drag induced by this flow. That is, let's say that, let's forget about edges that the flow doesn't use it. Okay. And consider this algorithm where let's say I just repeat doing this. Just do DFS to get an ST path. I do DFS starting from the source. Okay, it might go somewhere. Then I just try to do the first search. Okay, it might go in this direction. It might go in any direction. But the direction that it will always go forward. And it will end at T, no matter what, right? Because the flow path, you cannot go from S to T. So you will go from S, and then you will just end at T. And once you end at T, you get a path. It's a ST path. And just imagine that, let's say now I get a path. Let's say now I just delete these edges from my flow. So let's delete this path from the flow. So what do we get after deleting this path? Claim that after deleting the path, what you get is still ST flow with value less 1 less. So why is that? Well, to check if F is a flow, there is just 2 things that you need to check. First, capacity constraint. And here you delete something, so delete flow value, so the capacity is respected. Next, what is the next thing to check about whether F is a flow or not?
Conservation.
Flow conservation. And why is it the case that flow is conserved on every node after deleting a path? Well, because for every node here, the in degree and out degree, if it is deleted, it will decrease by the same amount. So what you get is still a flow. And the value will be less by 1 just because you see the out degree of S is now reduced by 1. So which means that, okay, you get a path and you reduce the amount of flow, the value of flow by 1. So you can just repeat this. How many times? Exactly the value of the flow times. Okay. And can you tell me also why is it the case that all the paths that we get from this, all of this iteration, why it must be edge disjoint? Can it be the case that I have 2 paths that share the same edges?
If you don't have an edge disjoint path, then 2 flows, both with like a flow of 1, would collide, and there'd be a flow of at least 2.
Right. So this is like we get edge disjoint really because we set the capacity of every edge here to be 1. Right. So there can be only 1 flow unit that goes through it on each edge. And once you once you have deleted, once you find a path and you delete this thing, like the flow value reduces from 1 to 0. Once you delete this path. So this an edge that some path have, that if an edge is used by some path, it will not be used again. So all paths are disjoint. And that's how we exactly, so that's why we get like a bunch of disjoint paths. Just to conclude, right? If you have ST flow, and this flow is 0, 1 flow, then there is a direct correspondence from this flow to many disjoint paths from S to T. How many? Just the value of the flow. And you can find this path in just linear time, linear in the size of this blue graph, because you just do the first search and delete edges in this blue graph. Each edge is visited once. Okay, so there is a direct correspondence between ST flow and edge disjoint path if the graph is unit capacity. So if you want many disjoint paths, all you need to do, compute max flow, right? Okay. So that's another problem we solve. Let's look at the same problem but in the undirected graph. Okay. So now let me ask the same question, edge disjoint path, but now the graph is undirected. Okay. So what I want is like a maximum set of undirected edge disjoint paths from S to T. So this is like one example. Okay. And so you have this kind of input. Now it's the undirected graph. In the flow problem, our graph is directed. But this is an undirected problem. What would be your suggestion on how to solve this problem? How would you try to reduce undirected graph to directed one? Any suggestion?
You make one that goes this way, one that goes that way for every edge.
Yeah. Yeah. Well, a quite natural thing to do is like for every edge, for every undirected edge UV, just make like two ways directed edge, right? Just kind of create two directed edge from U to V and V to U. Okay. So now at least the direction doesn't matter that much because every edge has two directions anyway. And let's see what happened when we try to work on this graph, right? Suppose now I just compute max flow in G prime. Okay, so you get some flow in G prime. And and also don't forget that I just put the capacity of everything to be 1. So an edge that maybe go this way have capacity 1, and another one has capacity 1 too. And now if I try to find a flow, now the flow actually can look like this. For example, it might look like it go in this direction. Another flow might look like another flow path. It might look like this, for example. So this doesn't look that good for us in the sense that this edge here, is now kind of used twice in the opposite direction, right? But intuitively, what we want is we want that each edge should be used once, so that it should correspond to some disjoint path. But now it's used twice. But I want to say that actually we can assume that this cannot happen. We can pre-process. We can process this flow a bit, so that this cannot happen. I want to say that actually I can assume that by looking at the flow and do something with it, then for every edge, the flow can go in only one direction. Either it's used only by one direction from U to V or from V to U. Okay. So there is a natural way to modify this flow that use this edge twice, so that every edge is not used twice, and you still get a flow with the same value. How would you do that?
Maybe put two nodes between, and the edge going forward uses the bottom one, and the one going back uses the top.
Yeah, actually, you said that, okay, just put two nodes in between, and then kind of make this kind of direction and this kind of direction. So now every edge is used just at most once, but still this path corresponds to this edge. This path corresponds to this edge, and at the end it seems like this edge is used twice. I really want that each edge should it be used more than twice. There is a simpler way to modify this flow so that you don't get this kind of situation. And after doing that, you still get ST flow. Very simple. More suggestion.
So when you put the flow into the graph, can you just delay the opposite edge along the way? Is that possible?
Opposite edge along the way.
Yeah.
That is about how to you need to modify the algorithm now. What I want now is you have some flow in G prime. I want to modify the flow in G prime such that each edge is used only by one, at most once. So just let's try to see this, right? What if I say that, okay, there is like a flow going through this directed edge and another one going through this directed edge? What if I say, okay, just make both of them 0? In some sense, it's like the flow kind of cancel each other. But why is it like, if I just make this from 1 to 0 on both of them, do I still get ST flow? Two things to check. It still respects capacity. Obviously, I reduce the flow value. Is it still like why is it the case that the flow is still conserved on every node? Just because for every node, the total inflow and total outflow, like they are the same except these two nodes. But for these two nodes, the in and outflow just reduced by the same amount. Just reduced by 1. So in and outflow on every node is conserved. Right? So just do this, like just look at every edge in like every undirected edge in original graph and just see if they are used in the 2 direction. If so, just delete the flow on both directions. You still get a flow. It's still a valid ST flow. Okay? Which means that now I can assume this. Each edge is used only by one direction at most. And in another way to see it, another way is that like each directed edge has only like 1 unit of flow going through it. It can be in either direction, but only 1 unit of flow going through it. Okay. But once you have that, then what do you get? You get a flow such that every edge is used once. Now just decompose it into paths using our path decomposition that we just described. Right? And this path, now they must be edge disjoint in the original graph, in the original undirected graph, because each undirected edge is used only by 1 unit of flow. Yeah.
So when you cancel the edges out to 0, why doesn't that affect like the max flow in G prime?
Yeah, because so the max flow in G prime, like what's the value of the flow in G prime? It is just the net flow going out of S. Right? And obviously if you delete edge, like if you cancel edge, cancel flow on this edge, it doesn't matter, like it doesn't affect the amount of flow on S. Also, suppose that somehow you like cancel flow on edges incident to S. Again, the net flow going out of S is the same. Right? So I just do this thing, like do some flow cancellation on like opposite edges, and then I get the flow that use each undirected edge only once, decompose it into a path, into a set of paths. And that will give you direct like edge disjoint path in the undirected graph. Make sense? Yeah.
How is there still going to be like an ST path? Because couldn't like hypothetically like every edge be like hit twice and then you cancel them all out with zeros? And then like how is there still like a flow there? I guess.
Okay, so I like there are 2 things that I need to argue after cancellation here, right? First, after cancellation, you still get a ST flow. It's still a valid ST flow. And that is the case because the constraint, like capacity constraint is valid. And the flow conservation constraint is preserved on every node still. So you agree that this is like a valid flow. Another thing I need to say is just that the value of the flow doesn't decrease at all. And why is that? Because the value of the flow is just the net flow going out of S. But can this thing change after this operation, after cancellation operation? No, because even if I do like some cancellation near S, like incident to S, after cancellation, both outflow of S and inflow of S will reduce at the same rate. So the value doesn't change at all, right? So after all this operation, I still get some ST flow with exactly the same value, except that each edge is now used only by one direction.
I see.
Okay. More question on this?
So does that mean that if you have bidirectional flow, it's the same as a unidirectional flow? Like if we just cancel out, I mean, we just
You can always like cancel, like it's not the same flow, but you can cancel them so that you still get a flow with the same value.
so basically you can just assume it's only a one-way flow.
Yeah, after doing this cancellation, you can assume it. Okay. Good. Right, so now I get a flow that each and undirected edge is used once, decompose it into paths. The number of paths is going to be the same as the value of the flow, and there are edge disjoint. And because you compute max flow, you get the maximum set of paths. Okay. Good. How about this one? Just minimum edge cut again, but in undirected graph, right? So you have S and T, and you want to find a set of edges such that after deleting it, now S and T are not connected by any like direction. Like there is just no path from S to T. Okay, now this one you should be able to suggest how should I solve it? Which graph I should look at again? How to reduce it to flow problem. Anyone? Come on. I want to ask many people. So you should volunteer a bit. Anyone?
Is it the same? Just like do bidirectional, like
Yeah.
go both ways?
Yeah. Like, let's just try to do the same thing. Like we have undirected graph. We know one trick. Just do the same thing. Create this bidirectional edges, and you have G prime. The next thing we should try to do is just here we want to cut, so let's try to compute min cut in G prime, right? And so now you see that a cut, an ST cut in G prime, well, it will be just some cut that's like separate S and T from each other. And now strictly speaking, ST cut in G prime, when you count, like this is G prime is the directed graph, so it will try to find a cut such that it minimizes the number of out edges from the cut. That's the strict definition of this cut in directed graph. So it minimizes the number of out edges. But now, for every edge, it's bidirectional anyway. So it will just minimize it, just edges that cross this cut. Like the number of edges that go out of the cut is just the same thing as the number of undirected edge crossing the cut. So if you find a min cut in G prime, it will just minimize the number of edges crossing this cut. So now like you get min cut that disconnect S from T. Okay. Right. So this class is just gonna be like this. Like we keep solving problem using MacFlow in one slide. Okay, so let's look at another problem now. I call it global minimum edge cut. Okay. So now I have undirected graph again, but there's no S&T anymore. What we want to say is we want to find a set of edges still, such that after you delete this set of edges, then the graph is not connected. So it disconnects some pair from each other, some pair of nodes from each other. Okay. For example, if the graph looks like this, maybe this is S, this is T, this is A and B. Here, a global min cut would be this one. You don't need to disconnect S and T. Okay. So, any ideas how we should solve this problem using many calls to MacFlow? Or solving many min cut, many ST min cut. There's one straightforward way to do this. Okay.
Try all pairs.
Yeah, you can try all pairs because this global min cut must separate some pair S and T. So let's try all pairs S and T and return the minimum one, like overall S and T, compute min cut, return the minimum ST cut among all ST. That's gonna be your global min cut. Right? So that takes n square MacFlow calls. That's good. So it can be solved in polynomial time. And actually, can you do better? Like, I claim that you can solve this problem using less than n square. You just need n MacFlow calls actually. How about n? Suggestion?
Could you like maybe call it on all n nodes and then the node with like the smallest degree, maybe, because like you can disconnect a node from the rest of the graph with the fewest number of edges by the one with like the smallest degree or something like that.
So that is not quite. So you suggest that maybe just take a node with smallest degree, but it can still be the case that it can be the case that there is just one edge here. This is the global min cut, but every node actually has like really large degree. So the degree itself is not that useful information for global min cut. But yeah, good suggestion still. Good intuition. Okay, you can try.
If you fix like an arbitrary vertex, it's gonna lie on one side of the minimum cut. So just fix one arbitrary and then try everything else.
Yeah, good. Yeah, exactly, actually. So one thing you can do is, let's say that I just fix some node S, okay? And then compute st min cut for all t and return a minimum one. That's the algorithm. Why it works? Why does it work? So I just said I fix some node S, okay? Try to compute min cut, st min cut for all t. Why is this okay? This is because, when you compute a global min, like, suppose that there is a global min cut. Global min cut might be somewhere, might look like this, might look like this. It must be somewhere in the graph, but it will disconnect S from some node, for sure. Like S is on one side of a cut in regardless. And this cut will disconnect S from some node. Let's call it A. And now whenever you range over all t, whenever t becomes A, and when you compute like st min cut, this is a global min cut, so it will be st min cut as well, right? So when you compute this st cut, you will be able to find some cut that is like as small as a global min cut, and that's why you're done. So like when you loop over all t, and when t is A on the other side of a cut, you will get a min cut, global min cut. So that takes just ON max flow. And actually, I want to mention quickly that for the state of the art, you can just do log n max flow. You don't even need n. And you can see the tutorial video here if you want to. Okay, so that's like one you can solve min cut, you can solve disjoint path. Now let's look at similar problem but for vertex version. Okay. So the problem is to find vertex cut. In this problem you have again directed graph. You have S and T nodes, node S and T, and from now I will say that a set V prime is a vertex ST cut if it's a vertex set, not an edge set now. It's a vertex set that doesn't contain S and T, and if I delete this set, then S cannot reach T. So I want to delete a set of nodes, which is not S and T itself, but after I delete that, then S cannot connect to T. Okay. So the goal is to find minimum vertex ST cut. Okay. So for example, these two nodes, this is a set that form vertex ST cut and is a min cut. Because once you delete these two nodes, then there is no path from S to T. Okay, So that seems now like quite challenging because, okay, how do you solve this using MaxFlow? Like MaxFlow is about like you have capacity on edges and you kind of delete edges. Now you want to delete a vertex. How do we do that, right? So let me just tell you the idea, the key idea. The key idea is again to create some graph G prime such that it has a nice structure. Like, so what I'm going to do is just to split every vertex U. Okay. Here, every node U is going to be split into U prime, U in and U out. And what I do is like I just connect U in to U out and I put the capacity of 1 between U in and U out. So that intuitively this looks like a capacity of a node now, right? Because like it's a capacity between node U in, U out. But this edge kind of simulate a capacity of a node somehow. And what I do next is that for any edge, let's say from U to X, right? I just connect U out to X in. And for every node that like that is like a in neighbor of U, I just connect, let's say A here, I just connect A out to U in. And the capacity here is infinite, like some big number. I just want this thing to be 1. Okay. So is a construction of G prime clear? Okay. So now let me ask you, like, so what I want to compute is like a sum, like I want to find a cut, like a vertex cut. And if you need to guess, like which cut I should look at in G prime, should I look at, like there are four variations of things that I want to look at. Which one should be related to our problem of computing vertex cut? So who think I should look at this one? How about number 2? Number 2, okay. How about number 3? Okay. Okay. Like, and how about number 4? Okay, so most people say number 3, and actually is the right answer. So good. So actually, if you look at any other cut here, you can even see that it has size 1 always, no matter what. Why? Because if you have S in, if you look at S in, it has just one edge going out of it to S out, right? And like, so all you can do just to disconnect S in from anyone is just to cut this guy, and like the cut size here is at most 1, always. Again, also for T out, you have T out. To disconnect some guy from T out, you can just cut this guy, and no one can reach T out. So only this guy has some non-trivial value of cut. And so let's see how to use it, right? So suppose that I just compute S out T in cut in G prime, call it A prime B prime. And suppose that the cut size is not infinite. Now, like you can observe that any edge that contribute to the value of this cut will always be of this form, from U into U out. Right? Because anything else here is infinite. But you assume that the cut is of size not infinite. So it must cut through this kind of edge. Right? The edge that go into it, you don't count it anyway. You count only edges going out of it. So now, edges that go out of the cut will be of this form. And that just kind of, now you can define a set of nodes naturally from this cut. For any edge going out from the cut A prime B prime is of this form, U in, U out. You just create a set of nodes U from all of this edge cut. Okay. And now you see that V prime must be a vertex cut, in a sense that if you delete V prime, now S and T cannot reach each other, right? Because, I mean, like S and T, S out cannot reach T in G prime, and and if you delete the edge of this form in this cut, then S out cannot reach T in. Meaning that if you just delete the node U itself, S cannot reach T as well. Yeah. Okay. And this set V prime is just the same, is just of the same size as the cut, the edge. Like this is a vertex cut that has the same size of the edge cut in G prime. So just to conclude, like you really have that S out T in cut in G prime just correspond to a vertex ST cut in G. And they have the same size. They really have their direct correspondence between each other. So given this correspondence, all you need to do is just to compute S out T in min cut in G prime. It will give you min vertex cut in G. All right. Question about this? Okay. So now let's see another similar question, like how about vertex disjoint path? So again, like I have directed graph and ST nodes. Now I want a maximum set of vertex disjoint ST path. That is, they cannot even share a node. They cannot like use the same node, but also other like except as the endpoint S and T. In other places, they cannot use the same set of nodes at all. Okay. So that's a similar problem to edge disjoint, but now it's vertex disjoint path. Okay. So what should we do? Well, can just try to do the same graph, look at the same graph, G prime, when you split every node to U in and U out, right? And now the natural thing to do is, now you want a set of paths. So you want, instead of cut, you want a flow. You just compute S out T in flow, max flow. And let me ask you, why is it the case that there should be animation. So it must be the case, right, that the flow on every edge here will be 0, 1. Okay. And the reason is that, like, even if like the capacity here is infinite, you still have that this thing should be -1 or 0, 0 or 1. And the reason is that, like, if you have a flow, it must go through, like, it must come from you out, but the flow can come to you out only through you in. So there can be only 1 unit of flow here. So the flow going out of you out can be only 1 unit. Just for the same reason, the flow that go into you in can come to you in only at most 1 unit. So every guys here have like either 0, 1 or 1 flow. Okay. And note that I just compute integral flow. So it's either 0 or 1 always. Nothing in between. And then, so now what do I have? I have a flow f prime, which is a 0, 1 flow in G prime. Like, it's a flow such that the capacity, like the value is 0 or 1. And which means that I can just decompose this flow into a set of H disjoint paths in G prime. Right? We saw that if the flow is 0, 1, you can just decompose it into H disjoint path. So it's a H disjoint path. We get a set of H disjoint paths in G prime. Still not in our graph, G. But I claim that just from this set of paths, now you will be able to get a set of vertex disjoint paths. And the reason is that the intuitive idea is just this. Okay, you have some H disjoint path in G prime, right? So this disjoint path must go through you in, you out at most once. So now, like, it's like you can use this guy only once. So just imagine that, okay, what I do in G prime, I just contract every edge u in, u out into u. Every path in P prime now is contract, like the path is shortened a bit. Now it will be a path in G. But now you see, for every node will be used by this set of paths only once now, because this edge is used once. The edge u in, u out is used once. So every node, this edge is used once, so the node u can appear just only once in this set of paths P. Okay. Yeah, so now you get that any flow here in G prime really just corresponds to a set of node disjoint paths in G. So if you want maximum set of node disjoint paths, so just compute max flow in G prime. Okay. Good. So what do we get here? We get that, like, this is like we just derive a well-known actually theorem by Menger. So you see that, so it says what? It says that for any graph, the minimum size of H st cut is the same as maximum number of H disjoint paths from S to T. I just told you how to compute both of them, H st cut and H disjoint path. But you see both of them, like, you really just compute max flow and min cut in the same graph. So they must have the same number. Like the value of both of them must be the same because min cut and max flow are the same. Right? Also, like for vertex connectivity, you have seen how to compute vertex mean vertex ST cut and vertex disjoint ST like vertex disjoint ST path. To do that, you just compute max flow or mean cut in this split graph. It's just the same, like the same graph that you compute. But max flow and mean cut are the same, so this thing must have the same value as well. So you see, like, and both of these just work in like both directed and undirected graph. So you see, like this theorem for edge and vertex, directed or undirected, these are just simple corollary of max flow mean cut theorem. Okay. And actually, let me just mention one thing. In class last time, we talked about max flow with edge capacity. Now it means that, okay, if you want to solve max flow with vertex capacity, you can. The only thing you need to do, the problem where you have a graph and ST, and now with vertex capacity, and you want max ST flow such that you respect the vertex capacity, like the total inflow on every node respect the capacity of a node, not of an edge now, it's not of a node for all you. You can just do this just by looking at, like, solve the flow problem in this split graph where you put the capacity between U in and U out to be the capacity of U. Right? So that's just how you can just, and once you solve the max flow in G prime, you can just contract U in and U out to each other and get the flow in G. And that flow in G will respect the capacity. Okay. So you see that max flow is really expressive in this sense. Like, you can just reduce it to, like, many problems reduce to it, and a variation of max flow, you can solve it using max flow itself. Okay. Question before I go to the next. So, all right. Next question about matching. So this scenario that maybe is quite familiar to you is maybe like, let's say this is IA, this is IA. So let's say that there are like n IAs, n people want to be IAs, and then there are another, but there are n IA positions, and each person is qualified only for the subset of the position. And what we want to do is like to assign as many position to as many people. Okay. So, well, this problem can be modeled as a graph problem. So it's called maximum matching. Well, matching is just a set of vertex disjoint edges. Maybe, yeah. And like, for example, this set of edges is a matching because they don't share any vertices. And the problem here is like we have bipartite graph. There are things on the left, V1, thing on the right, V2. Now we just, like, this corresponds to a set of IAs. This is a set of position. And what we want to do is now, like, this IA is is qualified only for these two positions and so on. And what we want to find is like a largest matching. Okay. So this one, for example, is an assignment from IA to the position. It's not maximum one. This one is maximum. So that's That's the problem of maximum matching. Instead of IA and position, you can think of like seller and buyer and like many like thing like so it's very like people really want to solve this problem. Okay. What can we do to solve this problem using MaxFlow? How would you try to solve this thing using MaxFlow? How would you create a flow instance from this graph? Okay.
Like, have the source code to V1 and then the sink comes from all the edges of V2.
Yeah, good. So you see, like, okay, there is no S and T in this problem, but intuitively we kind of want to kind of send or match a lot of things from the left to the right. So this intuition should give you like that seems like something that similar to flow, where you like here you want to match things on the left to the right as much as possible. But okay, there is no S and T. So what you should do? Well, how about just create a source and sink by yourself, right? Connect the source to every guy on the left. Connect the sink to every guy on the right. And set this to be, you have direction like this. Okay. And then let's say that I set the capacity of each node to be 1. Okay. And then just find MaxFlow. Okay. So once you find MaxFlow, you will get some flow. And you also know that like how does it look like? Well, this flow, every node will have just at most one flow going through it because it has capacity 1. Meaning that like if you just now look at the graph, now if you forget edges, forget the dummy edges and look at the original graph, the flow path that goes through it, there is only one flow path, and like these edges will be vertex disjoint, right? Because there is like the capacity is 1 on every node. So here, like here's the MaxFlow looks like this. There are only 2 edges, and they are vertex disjoint. You see, like. This is exactly like when you try to find like any ST flow really correspond to a matching in this graph. If you want largest matching, just compute MaxFlow. Yeah. Yeah. Okay, so that's it. That's like how we solve it. Yeah.
Wait, so this only works for bipartite graphs, right?
Yes. Yeah, this works only for bipartite graph. If the graph is not bipartite, you cannot just use MaxFlow. Okay. Now, so that's how we solve bipartite matching. Now let's try to derive some nice and well-known theorem about bipartite matching. Actually, the theorem is called Hall theorem, and it says this. Let's say that you have bipartite graph on where you have vertices on the left and on the right, and let's say vertices on the left is of size n, and there are r vertices on the right, maybe have size more than n. Okay. And for any set of node S, I say that the neighbor set is just like all nodes that have edges incident to it. So for example, this is my set S, then the neighbor set is just this guy because it is a node outside the set that have edges incident to it. So now, Hall theorem says this. A graph, we have a perfect matching, meaning that you can have a matching where every vertex on the left is matched to someone. If and only if, for every set on the left, the size of its neighbor is at least itself. For example, like this one, you actually have a perfect matching, and you can check that this is the case. And this is a graph where you cannot have a perfect matching because there is a set such that its neighbor has size less than itself. So no matter what, you cannot match these two guys, for example. Okay, so that's a statement of Hall theorem. Does it make sense, the statement? We will try to prove this theorem using Maxwell mean cut. So let's try to prove it. Okay. Good. So there are two directions. Suppose that there actually is, if there is some set such that this is the case, like neighbor set is strictly less than S, then that is trivial because like the set S cannot be matched. Everyone in the set S cannot be matched anyway. There are like less guys to be matched to. So that no perfect matching in this case. That's easy. But let's see the other direction. Suppose now that neighbor set of S is at least S for all set. Okay. Then I claim that if this is the case, then every vertex cut, every vertex ST cut, if you look at, now I want to prove this theorem using mean cut Maxwell mean cut theorem. So let's just look at the flow instant that we created with this S and T here. I claim that suppose that this is true, then any vertex ST cut must have size at least L. Okay, you will see soon why this is useful, but let me try to prove this. Okay. So actually, let's assume that this is the case for now, and let's try to prove it later. Suppose that is it the case that every ST cut, every vertex ST cut have size at least L? It means what? It means that by like Menger theorem, right, or Maxwell mean cut, if the ST cut is big, then there must be many edge disjoint paths, as many as the mean cut. Like ST cut is the same as number of vertex disjoint path. Like the minimum vertex ST cut is of size at least L, so the maximum number of vertex disjoint ST path is of size at least L. So you can find like L many ST path, vertex ST path to T. But that implies that you have a perfect matching. Because just look at this vertex disjoint path and look at the original graph, it corresponds to a perfect matching. So let's try to prove this thing, right? All we need to prove is that the vertex cut is small, is large. Well, why is that the case? Well, just consider any ST cut, vertex ST cut C. is some vertex set which doesn't include S and T. And now let's say that I call CL is just a cut, like just a guy in the cut on the left side. Okay. Like my cut might look like this. I just look at CL, all the cut nodes on the left side. And this is UL is just the uncut guy, the guy on the left, which I didn't cut. Okay. Now I claim that if I don't cut UL, then it just must be the case that I must cut the neighbor of UL. Right? Because if I don't cut its neighbor, then there is a path from S to T. If I don't cut this guy, every neighbor of UL must be cut, must be removed. Okay. So the neighbor of UL must be actually in the cut. But once I know this, then what do we know? Okay, then it means that the cut size, well, it contains the guy that I cut on the left, and the guy that I cut on the right must contain this neighbor of UL. So this is all the guy that I need to cut. But UL, neighbor of UL is of size at least UL. So C is at least CL plus UL. But what is CL plus UL? It's just L. Okay. So that's why we know that the cut needs to be at least of size L. Okay. Make sense? Okay. Okay, so now let me skip this actually. Let me talk about another question called circulation. So in this problem, it's like a generalization of Mach flow now. You have a directed graph, you have edge capacity, and now actually I have a vertex demand on every node. Instead of having like a special node S and T, now I have vertex demand on every node. Okay. And what I want to find is like to find a flow on every edge, so that first it must still respect the capacity, but now I will not have like a flow conservation. I want that instead of saying that for every node flow in equals to flow out, I want to say now that flow in minus flow out is dV, is my demand. Okay. So previously we have that only S and T have some like the net flow is non-zero. Now like I specify what is the net flow on every node that I want, and I want to find a flow such that it satisfies this demand on every node. And I want to find such a flow, or you just decide that this is impossible. That's my task. Okay. So, first question. Okay, yeah, not. So, is the statement of the problem clear? Let's see how to solve this one. So this is an example where you have like a 4 node with non-zero demand. Okay. For other nodes, like they still have 0 demand, and I have edge capacity. And this is one way to like, this is just an example how to define the flow such that this is an example of circulation. Like for this node, it has like an inflow, net inflow of 3. For this node, it has net outflow of 2. Okay. So the minus guy want to send some flow out of it. The positive guy want to receive some flow. Okay, so that's the problem. Let's see how to solve this using MaxFlow. The strategy is again, transform the problem to flow problem. And then we will try to ask, like, if the value of MaxFlow is something, then we say yes. Otherwise, there's no circulation. That's the strategy. So now, you see, this red guy, the minus guy, kind of want to send flow out of it. This green guy want to receive flow. Any suggestion on how do we like create ST flow instant from this problem? So, well, what I'm going to do is just add, again, some dummy sink, a dummy source, right? And then I just connect this like super source and then connect it to all the red guy. The red guy is someone that wants to send something out of it. So I just connect the source to it. And the capacity that I'm going to send, that I set from the source to this guy, is just, this used to be -2. I just set the capacity here to be 2. Okay, and the same for this guy. So the intuition again is like the flow is created, should be created at the negative demand node. So I just connect the source to it. Then do the same for the sink. The green guy will be connected to the super sink. The demand will equals to the capacity. Okay. And now you see, once I look at this graph, then what I'm going to check is that I can just check if there is a max flow from S to T such that the value of the flow is a sum of positive demand. If there is a case, it means what? It means that there is a way so that S send to flow here, send 4 here. And then this flow is routed somehow. And at the end, it will leave out of the green guy. The flow will leave the green guy to T. By what amount? Well, like this is like a, it will, this is like this thing sum up to 6. So this thing also sum up to 6. So it will leave here exactly 3 and 3. So you see, like, you get some flow, and then it is routed somehow in the original graph, and the flow will be originated from the red guy and left the green guy. So that is actually your circulation. Okay, so I have more things, but I don't have enough time. So then, yeah, you can ask questions about this thing, and we will continue with more example next time. Is this clear? Yeah.
So the edge to the red node with 2 is 2 the flow or the capacity?
This is the capacity. But what I want to check, right? This is the capacity, but then I try to find max flow. Okay? And I just check if my flow actually is just the sum of the capacity here. a sum of, let's say, negative demand. So if the value of my flow really is a sum of negative demand here, then it means that I find some flow that really saturate these edges. It really saturate the demand here. Okay. All right. Okay. Yeah, we need to continue next time on this thing. But yeah, so that's it for today.